Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we are discussing about we were discussing about the various ring form of that glucose, and in addition to that we have drawn how the ring structure of the glucose are formed according to Fisher projection formula, how to convert that Fisher projection formula into Haworth projection formula. There are certain rules for the conversion of Fisher projection formula into Haworth projection formula. Fisher and the Haworth, they are the scientist name. According to them, how to draw, how to represent the ring structure of the glucose, that we have learned in detail. So according to that, when the ring form of that glucose is formed, there are the different forms are obtained. One is called as a alpha D glucopyranose and another one is called as a beta D glucopyranose. Again the question arises, what do you mean by the alpha form? What do you mean by the beta form? Alpha form is nothing but at an anomeric carbon atom. Anomeric carbon atom means what? The electronic configuration, or what we can call it as in an optical isomer, they are differ only at the configuration. At anomeric means C1 carbon atom, and rest of the chiral center, they are having the configuration is the same, only the configuration are changed. At anomeric carbon atom means carbon number 1, which is the additional chiral center generated, which is the stereogenic center is generated when the cyclic ring is formed. And when, if you remember, the open chain structure of that D-glucose, there you will find, you already know that there are four chiral centers. When the ring structure of glucose is formed, one extra chiral center is generated due to the formation of the ring, and that at carbon number 1, that is called as when hemiacetal structure, ring structure of that alpha D-glucopyranose or D-glucose ring is formed. At that carbon, only the configuration is a change, one representing, one showing the configuration R, whereas another showing as a configuration is a S. So that type of the isomer, optical isomers of each other, are known as anomeric carbon atom, or anomer, we can call it as anomers of each other. They are differing in the configuration at only one carbon atom. That type of the term are known as anomers. Epimers and the anomers are same, but epimer is the word used in a open chain according to as a Fisher projection formula. For example, the well-known example we already learned, one is a D-glucose and another one is a D-mannose. Everything at a chiral center, their absolute configuration are the same, but only at one carbon atom, particularly in a D-glucose and D-mannose, they differ in a configuration at C2 carbon atom, and that's why they are D-glucose and D-mannose are epimers of each other. Anomers means what? When the ring, because why the rings are formed in an open chain compound, the scientists have analyzed these whatever chemical reaction or evidences, those are not fulfilling the some of the chemical reaction are not shown by the never shown by the open chain, and some additional chemical reaction are shown by the ring structure, and therefore ring structure fulfilling all the chemical or all the evidence of that type of the organic compound, and therefore we are seeing the ring structure of that glucose. So this is all about the discussion we already studied, but here I have repeated those points once again. Now let us move on to the next point which we are discussing right now. What is that point? Look at here, anomeric effect. What do you mean by the anomeric? Right now we know that anomers means what? The optical isomers, they differ in configuration at only one carbon atom, specifically at carbon number 1, which is known as a anomeric anomers of each other, and that effect is known as a anomeric effect. And due to that, what is happening? Because when the ring structure of the glucose shows the anomeric carbon atom, and whenever two form of that compound, that anomeric means alpha form and the beta form. Alpha form of a D-glucose and beta form of the D-glucose, we know that it is when the hydroxy group, those are lying on the right hand side, when these structure Fisher projection formula was used to represent the open chain of D-glucose. When that open chain of the D-glucose, when it is converted into, or even though cyclic structure of that glucose represented according to as a Fisher projection formula, that is not the better way to represent the ring structure of that D-glucose. It is better way of representing glucose molecule according to as a Fisher projection formula. And for the conversion of Fisher projection formula into as a Haworth projection formula, because Haworth projection formula is a better way of representing the cyclic structure of the glucose, and therefore how to convert that Fisher projection formula into the Haworth projection formula, there are certain rules. Rule number 1, whatever hydroxy groups are present, if those hydroxy groups are lying on the right hand side of the framework of that, or the carbon skeleton, we actually representing the Fisher projection formula while studying as a carbohydrate chemistry is vertically, and those are present or those are lying on the right hand side. They according to as a Fisher projection formula, they goes below the plane, means those are not below the plane. Let me clear point here. Those hydroxy group are lying on the right hand side, they goes below the plane, means from the alpha side, and those are those hydroxyl groups are lying on the right hand side, lying on the left hand side in a Haworth projection formula shown above the plane, in the Haworth projection formula. So these are the rule, we know that. And now is the anomeric effect. How that anomeric effect, where it is occur, what is the actual meaning of that anomeric effect, how the properties are changed, or we can compare the stability of that alpha form is more stable or beta form. I already told you at the beginning, when there is a formation of the alpha D-glucopyranose and beta D-glucopyranose, which form of the that anomer, whether alpha form is more stable or the beta form is more stable, at that time I already told you that I said there. So which form is the most stable, that we will study later on. Now it is a time, for the time being I am now explaining that point, why the alpha, whether the alpha form is more stable or beta form is more stable, what could be the reason behind it. Suppose as alpha form, anomer or alpha epimer, or what we can call it as alpha form, is more stable. Why it is more stable? What are the factor which that exhibit the stability of that alpha form? And suppose as a beta form is more stable, at what experiment, at what condition, what are the specific condition that the beta form is more stable than the alpha form? In what condition, what type of the group? And as we know that ring structure is generally stable form of the 6-membered ring, because when the 6-membered ring is formed, it involves 5 carbon atom and 1 oxygen atom form as a pyran ring, means 6-membered ring, 6 heterocyclic compound, 6 or what we can call it as a 6-membered heterocyclic compound, similar to as a pyran, which we already learned, which is a heterocyclic compound. And when it is a chair form is more stable, when chair form is more stable, and whatever substituent occur on at the 6 what we can call it as a 5 carbon atom, they having some substituent rather than the hydrogen atom, they are bulkier than the hydrogen atom. If hydrogen atoms are there, there is no question about discussing the stability of that chair conformation, because chair conformation is the most stable conformation of all other conformation. And as we know that conformation means what? Just rotating the carbon-carbon single bond, we are getting as a different type of the conformer. Different type of the conformers is known as a conformational isomers. For example, chair conformation, half chair conformation, twist boat conformation, boat conformation. So these are the some different conformation you already studied in your previous classes, but now here at moment here remember chair conformation is the most stable, and therefore while studying the whatever substituent present on it and how they get stabilized, and there due to the anomeric effect, why the anomeric effect occur here, that we are learning right now at present. Except for the hydroxyl group, a glycone group tend to assume the axial orientation rather than equatorial. For example, Lemieux et al. 1958 showed by means of NMR spectroscopy. As we know that NMR spectroscopy is nothing but as a nuclear magnetic resonance. H1 NMR and carbon 13 NMR, as we are known well, you already studied in your previous classes, as well as this I think 351 at this semester also you are learning that course parallel to this, and therefore there are the different spectroscopic method. They are the modern method for the elucidation of the organic compound, or what we can call it as a here specifically in the carbohydrate chemistry. So these are the advanced, or what we can call it, a modern method for determining the perfect correct structure of the organic compound, specifically in this particular is a carbohydrate NMR spectroscopy, and that this was the case for aldopyranose, in which the one OH group had been replaced by OMe, OAC and Cl. OMe means methoxy group, then OMe, then AC means acetyl group, OAC, that acetyl group, and chlorine. These are the sum of the group. Those are replacing by that hydroxy group and at anomeric position, and then what is going to happen, what type of the effect, and that effect is nothing but as a anomeric effect, remember here, and this has been called the anomeric effect and is believed to be due to the interaction between lone pairs of the ring oxygen atom and those of the substituent at C1, and this interaction is less for an axial than for an equatorial substituent, and alpha D plus pyranose is more stable than beta form is called anomeric effect. Understood this? The meaning of this anomeric, what do you mean by the anomeric effect? Now listen carefully. We are at the point where we actually discussing the anomeric effect, and now we come to know that for that purpose, to explain the anomeric effect, you must draw the alpha form as well as beta form, and after that let us see here. This is one of the form I am writing over here. Let's see. This is a chair form of this, and you might be knowing here this is a anomeric carbon number 1, where the hydroxy group is below the plane, means it is at alpha position, and therefore it is termed as a what we can call it as, it is termed as a beta position. Here first let us see here equatorial. First I am going to draw here. First one is the equatorial position. Here I am taking one of the group, that is the Z. Let us consider here Z, and now on the other side I am drawing another structure of this, the same chair form of that, and Z I am writing over here. And as we know that Z is nothing but, as any group we are going to consider, I am trying to explain the anomeric effect with the help of this suitable example. This is a suitable example I have taken, and now as we know that this is oxygen atom, heteroatom involved in this pyranose ring, and therefore here the orbital I am showing here is a like this. This is a lone pair which is present over there. Here when the bond present, when the substituent present at an equatorial position, there the orbital I am showing like this here. This is another any electrophilic or what we can nucleophilic type of the substituents are present like this. They are having the orbital which is lying like this, and when these orbital, there I am showing these orbital, there is a interaction, lone pair interaction over there. There is a lot of what we can call it as a interaction takes place over there. And if suppose Z is on this side and hydrogen atom we can put over here. Here the same lone pair which is present on oxygen atom we can represent. These orbital lone pair orbitals are lying in this manner or in this way. Now here Z group, this is lying like this. These are the orbitals shown over here. And look at here, the lone pair which is present on oxygen atom, and this group, they are very away from each other. There is no steric interaction, and therefore now if you consider over here, there is a steric interactions are there. If Z is equal to, suppose here, if Z is equal to OH, let us consider here Z is equal to OH, beta form is more stable. Here beta form is a more stable, and now when more stable, Z is equal to OMe, OAC or Cl, and if Z is equal to OMe, methoxy or OAC or Cl, chlorine, that type of the groups are there. They are the bulky group, and therefore beta form is a less stable here. Beta form is a less stable. Remember here. Now beta form is a less stable. When Z is equal to such type of the groups are present at an equilibrium position, then there is a lot of steric interactions are there, and therefore this beta form of the D-glucose is a less stable. Suppose there is a hydroxy groups are there, then and then bulkier group are what we can call it as it is preferred to stay at equatorial position, and therefore beta form of D-glucose is a more stable. When there is a hydroxy group which is at an anomeric carbon atom, when it is present at equatorial position, at that moment, at that time, beta form is more stable than the axial. Remember here, suppose here let us see here less stable, and now it is equatorial. This one is equatorial beta form. It is a beta form it is, and that less above the plane. This one is above the plane, and less stable due to interaction between lone pair. Is a less stable due to interaction between lone pair. That is it. And here if Z is equal to OH, which is present at axial position, where alpha form is a less stable here. Less stable. Here what is happening? Here 1, 2, 3 position hydrogen, there are lot of steric interactions are there, and therefore therefore alpha form is a less stable. When if Z is equal to OMe, methoxy or O-acetyl or chlorine, at that moment alpha is more stable. Why alpha is more stable? Because there is no steric interaction. This compound, this is present at axial position. When it is at axial position, the alpha form below the plane. This is alpha form which will be below the plane. This one is below the plane according to that Fisher projection. For more stable, no interaction. More stable, this one. More stable, no interactions. No interactions, no interactions of sigma, what we can call it as a non-bonding to sigma star interaction. That type of the interaction is not occur over there, and therefore this is the suitable example of which from that we can come to know that what do you mean by the anomeric effect. Once again, look at here. While explaining the anomeric effect, what do you mean by the anomeric effect? Let us see here. There are the I have drawn here the two structure. One structure is like this, another structure is like this, where here Z I am showing at equatorial position. In this structure, here the Z group which is lying at a axial position, and if here I am assuming that if Z is equal to OH, then beta form is more stable. Here Z is equal to OH when at alpha position. Here why it is a more stable, even though, because as we know that the general rule, though the chair form, the bulkier group prefer to stay at equatorial position, because when they are present at equatorial position, hydroxy groups are there, and even though there is a steric interactions are there over here due to that lone pair, but beta form is more stable and alpha form is less stable, because at when hydroxy group at alpha position, another effect, look at here, 1 2 3, there is one hydrogen atom and they create it as a they create 1,3 diaxial interaction over here, and here also 1 2 3, here hydrogen atom, they create lot of steric interaction or 1,3 diaxial interaction, and due to this reason this form beta alpha form is a less stable over here, but here beta form is a more stable. So that is called as the anomeric effect. If Z is equal to methoxy group or OAC group, acetyl group and chlorine group, because they are that hydrogen atom, in case of that hydroxy, this hydroxy, what I did over here, replaced by methyl group, acetyl group or chlorine group, they are bigger than hydrogen atom. When they are bigger, when they are present at equatorial position, such type of the bond orbital interactions are generated, and due to that orbital non-bonding interaction, they are insufficient space to, or they create a lot of steric interaction, and that's why the beta form becomes as a less stable. As if you see over here, the OME, OAC or Cl, there is 1,3 diaxial interaction is present over there, no doubt about it, but main controlling factor is that the oxygen atom and these group are well separated from each other. Don't think about here is a 1,3 diaxial interaction while explaining, and that's why it is nothing but as an anomeric effect. Anomeric effect, because if you assign the configuration of this anomeric carbon atom, carbon number 1, and it is also as a carbon number 1, it will have a different configuration, and this will also has the different configuration, and therefore these are the anomers of each other, and due to this reason they are showing different stability of that anomers, and that's why that type of the effect is known as anomeric effect. Understood this? Anomers, we know that in the cyclic form they the configuration is they differ in a configuration at only one carbon atom, specifically at anomeric carbon atom is known as anomers of each other. Epimers of that is anomers of each other. And if hydroxy group at anomeric position, it is present at equatorial position, the beta form is more stable than the alpha form, because when it is present at alpha position, when it is present at beta position, there is no such a type of the interaction at all, but when it is present at alpha position hydroxy group, there is a effect is introduced due to the 1,3 diaxial interaction, and that's why that alpha form becomes as a more stable, more unstable, because there is a generation or it produces as a 1,3 diaxial interaction due to hydroxy group and the hydrogen atom. They are at 1,3 position, they create a lot of steric interaction. But if Z group, if that hydroxy group of that hydrogen atom get replaced by methyl group, acetyl group or chlorine group, the stability of that conformer is exactly opposite or vice versa. Therefore, in this case, here the beta form will be dominant than the alpha form is a dominant, means major, over the beta form due to the presence of this group, because they when they are present at equatorial position, this type of the group, methoxy, acetyloxy or chlorine, they are the bigger group, and the non-bonding N2 sigma star type of the interaction is occur over there. They create a lot of steric interaction, and due to that reason the stability of that beta form is less as compared to the alpha form. So that is nothing but as a anomeric effect we have seen over here. Anomeric effect vary inversely with a dielectric constant of the solvent. As we know that there are two type of the solvents are there, polar and the non-polar. Among that polar and the among polar, aprotic polar and the polar protic solvent, these are two, and dielectric constant, those are having high dielectric constant, they are the polarity is increases, and therefore in aqueous solution anomeric effect is a small, because dielectric constant goes on, because anomeric effect vary inversely with the dielectric constant of the solvent, and therefore in aqueous solution generally, as the water is a very high dielectric constant it has, and therefore that anomeric effect will be very less. And because dielectric constant of water is high, in anhydrous methanol there is 50% of alpha D glucose and the beta, equal proportion of these two, that is in anhydrous methanol there is 50% of alpha D glucose. As we have seen, rates of the reaction may depend on the conformation, since the anomeric OH is more reactive than any other OH group in the ring. So this is all about the anomeric effect which we have seen here in detail. So tomorrow onward we will see the formation of the glycosidic, means ring structure of the glucose, why it is important than the other one that we will see. I think ring structure of the glucose on the basis of the chemical evidence, stereostructure of D-glucose was represented by the Fischer projection formula, and glucose however was found to exhibit some more chemical properties which could not be explained on the basis of structure first, and it was necessary to write another structure for glucose which will explain all the properties. Ring structure of the glucose fulfill these requirement, and that what is that requirement, how it is fulfilling that requirement, that we will see in the next lecture. I think with this let us stop, let us wrap up today's lecture over here. Thank you, have a nice day.